Okay, well, I'm going to do some examples from section 4.2. You'll need to have your book open to page 192, and I'm going to start with problem 2. And the function g of x is defined as x squared minus x minus 12. And if you look at the directions, I'm asked to find the local extrema, the intervals on which the function is increasing, and the intervals on which the function is decreasing. So I know I'm going to have to start off by finding the derivative, which is 2x minus 1. Since I know that this is a continuous function, for the derivative is continuous, I know that there are no places where the derivative is undefined, but I do need to set this equal to 0. So if I have 2x minus 1 equals 0, I get x equals 1/2. This is my only critical point. I have an open interval, so I don't have any endpoints to check. So what I'm going to do is mark a half. I'm going to be testing a point on either side and recording the values of g of x above this line. So if I plug in a 0, I get negative 12. If I plug in a 1, again, into my original function, I get negative 12. And if I plug in a 0.5 or a half, then I get negative 12.25. So this tells me that I have a minimum. So there's an absolute minimum at 1/2, negative 12.25. That's part A. Okay, now for part B. Part B asks, I'm going to do parts B and C really kind of together, because part B says to find the interval on which the function is increasing, and in part C, the interval on which the function is decreasing. Well, remember from the PowerPoint notes, your function is increasing. So let's say g of x is increasing when g prime of x is positive. Remember, g prime of x is the slope. If the slope is positive, my function is increasing. So really, when I want to know when is the function increasing, that's the same as solving the problem, when is the derivative positive. So I want to know when 2x minus 1 is greater than 0. So I can solve that. And I get x is greater than 1/2. So the function is positive. Now keep in mind that's not a contradiction here. Here I was plugging in the values back into my original function to show that this was a minimum. Here I'm talking about the derivative now. So when I set the derivative to be greater than 0, and when I solve for that, that tells me that the function is increasing. So g of x is increasing for x greater than 1/2. Or we could put that in interval notation and say this. And for part C, we have g of x is decreasing when g prime of x is less than 0. So that's going to be g of x is decreasing when x is less than 1/2. Or we could say negative infinity to 1/2. And that's what they were asking us to do. So you need to remember that when the directions say, where is the function increasing, what they're asking you to do, or what you're being asked to do, is find the derivative and find where the derivative is positive. Now, what you can do to kind of help with this little number line idea is mark your critical point. And here's g prime of x this time. We know it was 0 here. it was decreasing here, and it was negative, and then it was negative here, positive here. So this is called like a sign chart. It's called a sign chart, and it just kind of helps you organize your work so you can see, okay, the derivative's positive here. That means my function is increasing. The derivative is negative here. That means my function is decreasing. Okay, let's try number 11. Same idea, but a little bit more complicated problem. So we have h of x equals negative x over x squared plus 4. All right? And I have the same directions. Local extrema, interval where it's increasing, interval where it's decreasing. I'm going to start off by finding the derivative. Have to use the quotient rule here. So if I think of this as u, then u prime is negative 1, and the denominator, v prime, is 2x. So I get u prime v minus u v prime all over v squared. Okay, I'm going to simplify the numerator a little bit, distribute that negative sign. Here, this is going to make this positive 2x squared so we get x squared minus 4 over x squared plus 4 quantity squared. Hopefully I did all that right. Okay, so that's my derivative. So two things I need to check, because I need to find the critical points. So I need to know where is my derivative 0. So I'm going to start with that. Now, since I have a rational expression, to find where it's 0, set the numerator to 0. So I have x squared minus 4 equals 0. We get x squared equals 4. X equals plus or minus 2. Negative 2 and 2. Okay? From there, I need to know where my derivative is undefined. So I have x squared plus 4 equal to quantity squared equals 0. And some of you might actually just see this. In order to have 0 in the denominator, x squared would have to be negative 4. But you can't square something and get a negative 4, so it is not, it's not ever going to be undefined. So I'm going to skip that part. You could solve it algebraically, but you can also just say it's not ever undefined. Okay, so these are my only two critical points, so let's go on from there. All right, so here is my function, which was, let's see, this line represents h of x. So I've got, I went ahead and plugged this into my calculator, and I'm going to go to the table. I'm going to plug in, say, let me switch colors. Say I'll plug in a negative 3, a 0, and a 3 to check those. So if I do a negative 3, I get 0.23. Plug in a negative 2, I get 0.25. Plug in a 0, I get 0. A 2, I get negative 0.25. And a 3, I get negative 0.23. So let's see what that tells us. So we have, at negative 2, we would have a max. And it looks like here at 2, we have a min. So we have, and these would be absolute max or global max, and an absolute min. I'm going to go ahead and write it out. So we have an absolute max at negative 2.25, and an absolute min. I don't know why it is doing this. Okay. Well, sorry about that. Let me see what I can do here to salvage this. Okay, it's not going too well here, but an absolute min at the point 2, negative 0.25. So that tells us that portion of the problem. The next thing that we're asked to do is find where it's increasing or decreasing. So let me show you how we can approach that. My critical points are where my derivative is 0. So I'm going to still use those same points. Oops, negative 2. Okay, this is not the pin's fault. This is me. All right, so we have this. Now, all I care about is where it's positive, negative, or 0. So I know it's 0 here and here. This time, remember, we're talking about the derivative. So I need to know what happens to the left. So pick something to the left, say negative 3. You don't really care what the value is. You just care if it's positive, negative, or 0. So here was my derivative function. So let's go ahead and plug in a negative 3 up here. If I plug in a negative 3, I'm going to have 9 minus 4. So it's something positive on the top. And notice how in the denominator, I'm always going to have something positive. So I'm going to have a positive over a positive, which results in something positive. I don't really care what it is. To pick something in between negative 2 and 2, I'm going to pick 0. So if I plug in a 0, I get something negative in the numerator, and I'm going to get something positive in the denominator. So I have a negative over a positive, which is negative. Then pick something larger than 2. So pick a 3. You plug it into the numerator, you get something positive. Plug it into the denominator, you get something positive. So you don't actually have to work it out, so you don't even need a calculator because you can really work that out reasoning through. Then you need to interpret this. You cannot leave this as standalone as your answer to your problem. So I would have to say h of x is increasing from negative infinity to negative 2 and 2 to infinity on those intervals, since h prime of x is positive. You need to give your reason why. Don't leave that out. H of x is decreasing on the interval negative 2 to 2, since h prime of x is negative. And again, the reason's important. Okay, let me go through and show you problems 15 and 18 ask you, you might want to look at the directions in your book on page 192. I'm going to do an example similar to that, except it's not one from the book. So, but I have some function f of x equal to the square root of x minus 1 over a closed interval from 2 to 5. And what the directions ask us to do in exercise 15 to 18 is show that the function f satisfies the hypotheses of the mean value theorem. And the hypotheses of the mean value theorem, you can look back at your notes, has two things. One, it has to be the function has to be differentiable over that interval, which this is. We know what the square root function looks like, and we know that the square root, I haven't included anything outside of the domain because we can substitute in a 2, substitute in a 5, and we know that the square root graph has this shape, and so we know that it's smooth and continuous, even though that didn't turn out looking very well. So that part is satisfied, and we can state that in words. We could also state that we can find the derivative, and we can show things like the limit from the left, limit from the right. We could show that as well, but we can just appeal to the graph since we are familiar with that function. Then we also need to find, the other thing was that it was on a closed interval, which it is. So those two hypotheses, those two are met. So now the directions want us to find the value of c in the interval that satisfies this. So I'm going to have to start by finding f prime of x. Okay, let me rewrite this as x minus 1 to the 1/2. So then we have f prime of x is 1/2 x minus 1 to the negative 1/2. Or we could write that as 1 over 2 times the square root of x minus 1. So that's f prime of x. Now the directions are asking us to find where, for what value of c, so I'm going to substitute in a c here, would it be true? This is a, and this is b, because these are the values on my closed interval. So I need to evaluate the average value of my function, plugging in a 5 and a 2. So I'm looking for f of 5 minus f of 2 over 5 minus 2. Well, f of 5, if I plug a 5 in here, 5 minus 1 is 4, square root of 4 is 2. Plug in a 2, and you get square root of 1 is 1. I took that interval on purpose, can you tell? So we get 1/3. So then I'm looking for what value of c would this be true, equal to 1/3, which is this part over here. So I'm solving for this now. So I want to know what the answer to this is. Okay? So we're solving for the c minus 1. We could do cross products and say 3 equals 2 times the square root of c minus 1. I can divide both sides by 2. I get 3/2 equals the square root of c minus 1. I could square both sides, and I get 9/4 equals c minus 1. And I could add 1 to both sides, and I get 13/4 equals c. So this would be the value that would, for this particular value, which indeed is in my interval, that would be the value where the average slope equals the exact slope, or the instantaneous, if we want to think of it that way.